So for our project, we decided to reverse engineer my old laptop, where my dog Misty wiped out the keyboard, which is the main reason why I stopped using it in the first place. So what better way to put it to good use than to reverse engineer it? At first, we had a little bit of trouble taking it apart, as some of the screws were hidden underneath the rubber feet. So after 30 minutes of trying to take it apart, we finally got the cover undone.
Honestly, it's kind of a smart move to put screws underneath the bumpers since it makes the outside look slightly more aesthetically pleasing, which is good for consumer benefits, and also prevents those screws from somehow coming loose on the very small chance that all the visible screws somehow failed.
Although true, it didn't really help us with our project much. Alright, so now we finally removed the rubber feet. So now all we need to do is take off all the rubber screws from the bottom of the computer. All we had to do is take a screwdriver and remove all the screws and lift the back of the computer to reveal all the parts. Though it wasn't that easy because we didn't have the best screwdrivers at the time, so we actually had to delay it another week just to get better screwdrivers to take the computer apart. Ah, yes.
All right, so is this the fan?
Yes, this is the
Okay,
CPU fan.
Yeah. That's the little thing that makes noise when I'm working.
So this is... Alright, awesome. We finally got the computer open. You can immediately see all the specs inside of the computer, such as the CPU fan here, the hard drive here, and the battery here.
So, one of the first things that had to be removed was the battery. It's a lithium ion battery, which is pretty standard for most household electronics such as phones, laptops, you get the idea. Lithium has a very low density, which makes sense as it's the lightest metal in the periodic table, actually the lightest solid. I mean, its atomic number is 3, which puts it right next to hydrogen and helium in weight, but lithium's electrochemical potential and subsequent ability to hold a charge is what makes it really ideal for batteries. Its lightweight nature certainly is a plus, though, because if someone managed to make a laptop battery out of osmium, well, let's just say lifting that laptop would be quite the workout. The battery hooks into fins that look quite similar to the ones on the heatsink that we'll see later. They serve an entirely different purpose, though, as they connect the battery to the rest of the laptop circuit. The battery was also hooked in with some screws, which again just gives you the extra security of knowing that the battery won't somehow come loose and go flopping all around the rest of the computer.
Alright, now it's on to the central processing unit. The CPU is like the brain of the computer, as it runs and performs everything in the system. This particular CPU is an Intel Core i3, which has a base frequency of 2.4 GHz and a maximum memory capacity of 32 GB. This particular CPU also has integrated graphics, so it really does everything in the system. It can support 4K up to 60 Hz, but the other specs won't allow it to do that, unfortunately. For the CPU to go into the motherboard, it has to be connected with all these pins. This particular CPU has 939 pins, which is a lot, especially for how small the CPU actually is. The CPU also has 2 cores, which means it basically has 2 brains. It can do 2 things at once, such as calculations and other processes. Other CPUs can have up to 48 cores, which is insane. Those are usually used for CPUs that are in control of huge servers. Most CPUs used by consumers only have 2 to 12 cores, though. Although 12 cores is still a lot. The materials made with CPUs are silicone, plastic, and copper. The silicone comes from either silica sand or from quartz, and the copper just straight from the earth. Oh yeah, I almost forgot to mention. You see that little spludge right there on the CPU? Yeah, that's actually called thermal paste. It keeps the temperature of the system under control by putting a layer of goop in between the metal-on-metal contact when it's all put together, so you know, it doesn't catch on fire. Now for the random access memory located here on the motherboard. The RAM's purpose in the system is to store active data. This allows the CPU to quickly and easily access the data for faster speeds with little to no hassle. This particular RAM stick has the capacity of 4 gigabytes, which nowadays isn't very much, and a speed of 2400 megahertz. It's also a DDR4 stick, which is the latest generation of RAM that is connected to the motherboard with 260 pins. Though not as much as the CPU, it's still a lot. Also, fun fact, once the system is shut down, the data that was stored in the RAM gets deleted unless it was transferred to long-term memory, which is the hard drive. Now for the long-term storage, the hard drive and the solid-state drive. In this build, I didn't even know there was an SSD in it. Though it only has 16 gigabytes of storage, it's in the form of an M.2, and I'm guessing its purpose is just to have Windows on it, which is the operating system. Now, the hard drive and the SSD. You might be asking, what's the difference? Well, the difference is how it stores the long-term memory. The HDD stores it on a spinning platter that the actuator inscribes the data physically onto the platter, as the SSD stores the memory into flash memory chips for faster and quieter access. HDDs are usually cheaper and have more storage, so you usually want the SSDs for things you want for fast loading times and HDDs for mass storage. Now, the SSD is made up of its chips and materials the same as the motherboard, but what about the hard drive? Hard drives are usually made up of metals and magnets, which uses the magnet head on the actuator and the magnetic coat on the platter to read and write data magnetically. It's a really fascinating way of storing and saving data even after the system is powered off for long-term storage. Though hard drives are now on the decline in the market because of SSDs. SSDs are just way faster and way more popular than hard drives nowadays, which is why it's on the decline. Yes, the motherboard. The motherboard is really what makes the system do what it does. The motherboard is made up of all these metal components and wires that connect each and every part to one another for a stable and reliable system. The motherboard is made up of fiberglass and copper, where the fiberglass is the insulation and the copper is the conductive pathways that sends messages from one component of the computer to the other. The motherboard is like the glue to the bridge, or like the team mom of your local kid's soccer team. It just makes everything run quickly and smoothly.
Another part of the system is the heatsink, which serves to cool the system alongside the fan. It's a very important part for temperature regulation and keeps the system from overheating or essentially frying itself. The heat from the system is transferred to the heat pipe, which has a liquid in it and a sort of wick. When the liquid is heated, it boils and evaporates in the pipe. That vapor then moves to the other end of the pipe, which is then cooled and recondensed back into a liquid by the fan blowing through the heatsink's aluminum alloy fins, which are there to absorb more heat as they have a comparatively large surface area and can therefore transfer heat away from the CPU faster, and the cycle continues. More heat goes into the pipe and heatsink and away from the CPU. The pipe itself is made of copper, which has very high thermal conductivity and a low specific heat. Copper is an excellent conductor and has a low cost to implement, which from an engineering standpoint makes it a wonderful option for heat management, not only for its efficiency, but also for the purpose of frugality. Engineers look to improve efficiency at a low cost, and using copper for a heat pipe as opposed to other materials accomplishes those goals. But aluminum alloys are even cheaper than copper, which is why they make sense for the fins for the heatsink. Since there's already a copper heat pipe in place to do a lot of the heavy lifting in terms of the heat exchange process, it's unnecessary to use copper, which is more expensive and slightly heavier for the fins of the heatsink. If the heatsink were for a larger machine that produced high amounts of heat, then copper might be necessary for the fins. But given that laptops such as this one do not produce levels of heat that require top of the line heat exchange systems, aluminum alloy works well enough and makes more sense for their intended purpose. The laptop's fan is powered by the battery and produces only about 15 decibels of noise when on. To put that into perspective, that's right in between the sound of breathing, which is about 10 decibels, and the sound of a whisper, which is about 20 decibels. It makes 5,000 rotations per minute, working at around 5 volts of electricity on average, with a 4-pin connector and weighing in at less than an ounce. The fan's blades are made of plastic, and the wires are very small and run into a single connector. I think the design could be improved though, because the fan seemed to collect dust and debris pretty easily, and it even got into the nearby heatsink a little bit, which seems bad considering that those areas are used as part of the heat transferring system. If I were in charge of the design, I'd probably try to implement some sort of fine metal mesh either over or underneath the current slotted design on the outside cover, which could actually absorb a little more heat while also preventing debris from entering the laptop and making cleaning much easier for the consumer. As it is now, they'd have to not only take off the cover on the base of the laptop to get to the heatsink for cleaning, and then clean out the fins and between the individual blades of the fan, which the layman might not think to do, therefore also exacerbating the issue by not fixing it quickly, which could damage the device if the heat exchange system is so adversely affected by the debris that the CPU overheats. If there were some sort of mesh covering these parts and preventing dust from getting past that, then the consumer could simply clean the mesh as opposed to having to pay close attention to detail and clean out tiny parts with something like pressurized air, which the average person might not even have in their home. But again, it seems to fall into the category of working well enough, like using aluminum alloy for the heatsink fins being good enough for the laptop's intended purpose and expected heat output from the CPU. The screen is made out of two main components. The first is the polarized glass, which is the outermost portion of the screen and is the reason we can see this display at all. This model laptop, like most models nowadays, uses LCD or liquid crystal display, which means the other component is another polarizing filter covered by a layer of liquid crystals. A backlight display that can display red, blue, or green then runs through the first polarizing filter, the liquid crystal layer, a color filter, and then the second polarization filter. We actually first found out the glass was polarized because I had some polarized sunglasses, and when I turned them to be about 45 degrees of an angle, it in front of the glass, it darkened substantially, as is typical of two pieces of polarized glass interacting with each other. Polarization works by basically filtering out light waves that are oriented perpendicular to the polarizing filter. Matt actually mentioned to me that he'd seen a video by LSO Physics where the creator made glasses out of pieces of the screen, and while wearing the glasses became the only person to see what the laptop was displaying, with the negative image visible with her head tilted one way and the positive image visible in the other direction. I hadn't expected the polarization because honestly, I'd never thought much about how a screen works before this project. Also, finding out that LCD means liquid crystal display was surprising too, especially upon the discovery that liquid crystals are just substances that share properties of liquids and solids, which I knew absolutely nothing about before. I guess that just solidifies the idea that we were completely and utterly lied to when we were told about the three states of matter in elementary school. Solidifies. And don't even get me started on the fact that the glass on its own is a supercooled liquid. My dad told me that when I was little, and it totally blew my mind. But anyway, looking at the screen in two pieces, I was really shocked at how simple it looked. I guess I was expecting to see a jungle of wires crossing over each other, sort of like an Arduino breadboard project. The other component didn't surprise me much. I could tell what their purpose was and how they looked, and I know that the data utilized by the screen to produce the display comes from the motherboard, but it was still shocking for some reason to see so little of what my brain associates with the term technology, like rubber coated wires and pins and metal and silicone and plastic, all rolled up to make a functioning system. So seeing just like a couple visible components of the screen was really surprising, I guess.
So when we were taking apart the laptop, the first challenge we had, and the most notable possible mistake in our disassembly of the laptop, was not initially realizing that there were screws underneath the rubber bumpers. At first, we kind of speculated that maybe there was some adhesive keeping it together, and that led to a conversation on whether it'd be easier to get a heat gun or a hairdryer, which surprisingly was not a straightforward answer. But after that first day, when we also realized that the screwdrivers we had were terrible for what we actually needed, which was working screwdrivers, The laptop still turned on, so our tugging at the partially screwed on cover couldn't have damaged it too much beyond some superficial damage to the plastic of the outside cover. So the next time we worked on it, we came equipped with better screwdrivers that actually had handles and took apart the laptop much quicker than when we were struggling just to unscrew things. The laptop is mostly comprised of magnesium, which makes up 22.7% of its mass, followed by borosilicate glass, inorganic glass, polycarbonate, and acrylonitrile butadiene styrene, or ABS, which make up 9.4%, 9.0%, 8.8%, and 7.3% of the total mass, respectively. Honestly, the only thing that really surprised me there was the magnesium. But apparently, magnesium is really good for the outer shell of laptops because it's light but also really strong, with a density of 1,738 kilograms per cubic meter and a Brinell hardness number of 260 megapascals, or 260 million pascals. Specifically, magnesium alloys are used, which are mixtures of magnesium and other substances, which are then solidified in a mold with the necessary shape and generally cost anywhere from $2.60 to $11.40 per kilogram. Borosilicate glass mostly consists of silicon dioxide, but includes many other oxides and is very flexible. It is scratch resistant, which makes sense for consumer laptops. Polycarbonate is fire resistant and lightweight, which makes it a good laptop material since they can get a little warm sometimes, and nobody wants a really bulky laptop, especially one that's on fire. ABS has similar attributes of durability and flame resistance and can be made into alloys with other materials to enhance those properties. These materials make up around 57% of the entire laptop, with many various elements and compounds making up the other 43%. All in all, the versatility of materials used just shows how the laptop was developed gradually for optimal performance. Over the years, Hewlett-Packard has tested the best materials to be used for different applications within their devices. The broad range of materials is evidence of this because heavy repetition of materials would indicate a hesitance to branch out and find better solutions. Even looking at other models HP has created, the material compositions are rather different from the model we worked on. Engineering is an ever-evolving field that focuses on bettering the technology available to this world, and this project has shown us just that.
Does she turn on? The answer is no. Okay, bye.